Hello everyone, welcome to another episode, and today we're gonna be doing this physics question. So yeah, let's get straight into it, right? Is it day, wait, I forgot to say what day is it. It's day 24 everyone. It's day 24. We have come a long way, and my physics skills have greatly improved, which is really good. Alright, so I'm just gonna keep doing this, alright, until maybe I become like next Einstein or something. I don't know. Probably not, but yeah, let's do it. So question number 8. A, state the two conditions necessary for an object to be in equilibrium. So two conditions for an object to be in equilibrium. So first thing, let's talk about forces, right? So there has to be a resultant force or a net force of 0 for an object to be at equilibrium. Remember that equilibrium means that there's no net forces, and so that means that object may be moving at a constant velocity, but that velocity isn't changing. It may be at rest at 0 velocity, but if it's at equilibrium, it's not gonna change from 0 to something, right? It's gonna just stay at 0 meter per second or something like that, right? So yeah, that's the key idea, right? And another condition to be for an object in equilibrium is about moment, right? So if you have a balance beam, and then if you have a pivot in the middle, then if the two forces on the left side and the right side are the same thing, that means that the moment for the counterclockwise position and the moment for the clockwise position is the same thing, then the beam will perfectly balance, and that means that it is in equilibrium. So those are the two conditions needed for an object to be in equilibrium. Alright, so let's go to question number B. And question number B is gonna be about like calculations. So let's do it. So a metal rod of length 90 centimeter has a disc 24 centimeter, radius of 24 centimeter, fixed rigidly at its center as shown in figure 4.34 right here. Right. The assembly is pivoted at the center. Right. So what's happening, right? It's gonna be like maybe 90 degree. The rod length is 90 degree, and the radius is only 4 centimeters, and then the disc is directly in the middle, directly at the center of this. Okay, so yeah, let's read the other end of the question. Two forces, each magnitude 30 Newton, are applied normal to the rod at each end so as to produce a turning effect on the rod. So here are the forces. So right here, on the edge of the rod, right here. So these forces will create a couple force. That means that it's like a balance beam, but there's no pivot, right? So and then those two forces will create a torque, and torque is basically like moment, but torque is basically like moment, right? So these will create a moment or a torque in a clockwise position, so the whole thing will move clockwise. So this will create a torque, and then a rope is attached to the edge of the disc to prevent rotation. So this is a disc, alright, and then there's a rope right here. I don't know if you guys can see it, but there's a rope here with a tension force like this. Okay, good to know. Alright, and then you have to calculate the torque of the couple produced by the 30 Newton forces and the tension T of the rope. Alright, so let's start with question B1. Alright, so a formula for calculating the torque of a couple means there are two forces that are parallel to each other, but they're in opposite direction, and those two forces will make the object spin at its center, like right here, right? So normal moment equation is gonna be force times distance from perpendicular distance from the pivot, but this doesn't have a pivot, so and instead the torque, or QUE, the torque is gonna be force to my tablet is lagging. Force multiplied by the distance between these two forces, that is going to be the torque. So distance between, I'm not gonna write it, I just write D as a distance, and this distance is the distance between the two couple forces. So in this case it will be 90, right? The force here, the force is here. So yeah, so the force is 30 Newton. Oh yeah, and the couple needs to be at the same force to work, right? Yeah. So this is gonna be 90 meters, I think. Centimeter. Centimeter. So this will create 27,000 Newton centimeter. So yeah, Newton centimeter, and this should be the torque of the whole assembly. You could say that. Okay, so number 2, question number 2, the tension T in the rope. So let's analyze this question a little bit. Let's analyze this assembly right here. So if the rod spins, the disc is gonna spin too, because it is fixed rigidly at the center. Alright, so and then, like I said, torque is the same as moment, right? So this whole thing is gonna have a clockwise moment of 27,000 Newton centimeters. Newton centimeter. Alright? So this is gonna be moment. So that this is going to have 27,000 Newton centimeter on my bad centimeter. So we can use normal balance beam equations for this, because for a normal balance beam to work, right? So a balance to work is gonna be like moment equals to force times perpendicular distance, right? And why don't we find that? It's because this is a tension force, right? And tension force, for a tension force to make the disc stop spinning, then it needs to give the same amount of force as this kind of force, right? What do you call that? I forgot. Angular velocity or something. I don't know. Angular linear velocity. I don't know. So yeah, this force, I'll actually use a different color for this. So this will be the force, and this force, the blue one and the red one, should be the same. So that this stops spinning, right? So you need to calculate this blue thing or something like that, right? Oh, we don't need to actually. We can think it differently. Like my bad. This is the center right here. Right, you think of it like a balance beam. Imagine this is the pivot, and the pivot is not here, but imagine this is the pivot right here. And then this is a perpendicular distance between the pivot, as you can see. Alright? And this is radius, so it's 24 centimeter. Okay? And this is perpendicular distance, right? So this force will create a moment of anti-clockwise, whilst these couple forces will provide a clockwise moment. You see what's going on here, right? So for this to be an equilibrium, the tension force needs to give the same exact moment as the clockwise moment. So by using that, we can calculate the force of the tension, and then we don't need to split the vector here, because this is a perpendicular vector. Perpendicular distance is 24 centimeter. So we can use the normal moment, or in this case it's torque, but it's basically the same thing, so I just write it like that. And then we have force times distance, perpendicular distance to be exact, right? So yeah, A and C distance. So you can see the normal torque for a couple force distance and the torque for a single force distance is the same thing. These two distances are very different. So yeah, that's the catch right here. That's the catch. So distance is 24 centimeter. We don't know the force. Let's give it F. And moment is gonna be the same as this. 27,000 Newton centimeter, right? So yeah, it's just, it should be a centimeter. Yeah, okay. And then the force is gonna be divide these two values, and then this should get to it. Again, let me take out my calculator. I am not ready for this. 27 divided by 24. Okay, it's about 112.5 Newton of force. So the string, or so the rope, needs to give a force of 112.5 newtons to make that the wheel, or to make the assembly stop rotating. Right? So yeah, that's gonna be the question. So 112.5. Okay. So yeah guys, so this is it for today, and I'll see you guys tomorrow. Tomorrow we're gonna be doing some, maybe we'll just keep doing these types of questions, or maybe we can move on to energy, work, and power. I'm not sure. Because yeah, these are A-level physics right here. Because I'm still in O level, but like I am interested in physics, so I am doing A-level ahead. So I'm going like by chapter. Like this is chapter, I think 5 or 4. It's in chapter 4. Next chapter is gonna be energy, work, and power. I already did the chapter today, so maybe we can do those questions tomorrow. I don't know. I'll see. But I really like doing these questions, so yeah, maybe I'll just keep doing these questions. There's 2 questions left, so yeah guys, so I hope you guys have a great day. Goodbye.